So our first presentation is going to be via Zoom from Dr. Alexander Aksenov from the University of Connecticut. We're excited to welcome him from there. He's a leading researcher in innovative pest control methods. He will introduce groundbreaking work on biologicals for the Asian Citrus Psyllid, leveraging graphene-based materials to create a powerful scent lure. The topic of his talk is developing a novel low-cost lure device using graphene-based materials to release the scent compounds that can attract or repel Asian citrus psyllid. This technology supports the attract and kill strategy, offering potential applications for integrative pest management in citrus nurseries.
Hello?
Yep. Go ahead, Alexander. We can hear you.
Okay. Do I share my slides?
Yes.
Okay. Shall we begin? A little bit ahead of time. I had a schedule.
Yes, go ahead and begin.
All right. Thank you, and I appreciate the invitation. I wish I could be there in person. I love California. I used to be there. Fortunately, I have teaching commitments, so I couldn't make it. But I'm really happy to talk to you a little bit about the project that is still ongoing, and this is something that a really good platform to also seek for feedback, because this is actively developing piece of research, and there are some implication and practical applications, and I really want to have feedback from growers and people who are actively interacting with growers. So my name is Alexander. I am a faculty at the University of Connecticut, Department of Chemistry, and this is a joint project with many people, but the key ones are Lucas Stilinsky at University of Florida and Ali Baz and Douglas Adamson here at UConn. So we are developing a technology for generating attractive scent for Asian Citrus Psyllid, but it's more broadly applicable than that, and I'll talk about that a little bit. Okay, so first off, motivation, and I don't think I have to explain to this audience what's the importance of pest management for home being, but basically in the pathosystem of the Candida albicans, the pathogen, the vector, Deferina citri, and the disease. If we targeting pathogen, the approaches such as bactericides, antibiotics application, things like that. If we targeting vector and the vector control, we're trying to eradicate ACP, or at least manage the population of ACP. And then the disease control, we're trying to maybe supplement citrus with citrus trees with nutrition and things of that nature. So we're focusing on the vector, and the vector, I believe, and I've been told multiple times by people who know the subject, vector is the key to all of these things, because it's not just a it's not just a vector for clone being, but it's also a major pest in itself. So those are slides from Lucas Stilinsky. This is an experiment they did in Florida a couple of years back, where the tree, even if it's healthy, if it's exposed to ACP, especially if it's continuous exposure when the ACP is feeding on it, it's really damaging to the tree. But then, of course, in combination with Huanlongbing, it becomes lethal. So management of ACP is a key, not just to control or eradicate Huanlongbing, but also to suppress vector population, even if or when we do eradicate HLB and find a successful management strategy. So the control of ACP is a topic that has been discussed quite a lot, but there is really not a solution that is a silver bullet. So of course, the first one we think about is the application of pesticides, and ACP requires fairly intense pesticide use. There are multiple problems with this, of course. First off, it's expensive, right? So this is not something that is sustainable, and the last I heard in Florida has been discontinued for quite some time because it's just economically not viable to continue to spray pesticides. Then it eliminates populations of natural enemies, and there's multiple other externalities. It's not just we're wiping out all the natural, flora and fauna in the orchard. There's all kinds of other things. We contaminate water supply. There are people who can get exposure nearby, and some of these pesticides are pretty nasty. Some of them remain in ecosystem for years. And the degradation products are poorly studied as well. We don't really know the health effect of that. We do know that pesticides, especially the ones that are long-term pesticides, are linked to all kinds of health problems. And this is something that we want to eliminate as much as possible if we can. And then, of course, it leads to resistance. Continuous spray with pesticides will lead to eventual resistance of the insect to the pesticide, and the pesticide have to be switched, kind of like we're racing against time with antibiotic resistance, or bacteria constantly developing resistance to new antibiotics. And unless we're developing new pesticides all the time, the insect is staying one step ahead of us. The problem with this, of course, is that every single time we do develop new pesticides, we need to be absolutely certain that it's it's not damaging to ecosystem, it's not damaging to human health, and those are large, substantial research questions that we might not be able to answer in time. So basically, this is a unsustainable path forward, and this is used as a stopgap, and we need to find a better strategy for ACP biocontrol. So a alternative technology that has been proposed a while back, and it's a very promising one, is to use and track and kill trap. So instead of spraying pesticides indiscriminately across all of the orchard, we place pesticides in a trap, and then we place the trap in the orchard, and then we have insect finding the trap, feeding on the bait, ingesting pesticides, dying off, and this way we're minimizing both exposure of pesticides to the natural, insects present in the orchard. We don't have to use as much pesticide, and we can use much more toxic pesticides because we don't get exposure outside of this bait. There is a problem with this approach for ACP specifically. So we do know that ACP is attracted to, like, for example, lime, green, yellow color. We do know bait that is really palatable to ACP. So it gets a gustatory cue when it's feeding on it, and it remains feeding on it to ingest sufficient amount of pesticides to die. However, what we do lack is the large range attractant, the volatile cue that is perceived by ACP on the long term. So it's actually attractive, and it makes its way to the trap itself. And this is an active area of research that's going back a few years ago. We do know that ACP is attracted to volatile cues. We have evidence that first off, of course, we do know that the citrus flush, especially young citrus flush, is the most attractive smell to ACP. And creating this smell is really difficult because it's a very complex smell made out of hundreds of compounds, and some of them may be very important to ACP. And in our research, we do know that we can actually trick ACP into being attracted to synthetic smell. But this is the paper that was published, a few years back, or 10 years back already at this point. We do know that ACP is attracted to the synthetic smell. However, we found that when we take a complex smell and we reduce it to only a few components to simplify and make it less expensive, ACP is quickly losing attraction. So it's something that has to be complex to be representative of the actual citrus smell. And also we found that even slight difference in ratio of certain volatiles is immediately leading to attraction to be diminished. Both of those are really problematic because, some insects are easy. Some insects are attracted to one thing. Like in Lucas Telinsky's lab, they have research where looking at ambrosia beetle that is attracted to just one single compound, and it's really easy to have this push-pull system when it's attracted to one volatile, and then repelled by other volatile to sort of siphon all of those beetles from the orchard. It's not the case with ACP at all. ACP is really persnickety, and this is something that has been continuous challenge for some time. We do know that if this smell is generated, insect is very, I shouldn't say very, reasonably attracted to the smell source, so it can be used as a lure to be placed in the attract and kill device. So the problem then is engineering. It's something that is difficult or borderline impossible to implement on the current level of engineering development, because the technologies that we have, the weak-based technologies or they are inadequate. And the reason why they're inadequate is this. So this is to oversimplify this problem a little bit, but this is just to make a point. So think of the way how the wick is working. We have a mix of volatiles that are comprising our blend, and then we disperse them using some kind of wick mechanism, essentially boiling this off. So first off, we cannot modify the mix composition. So once we are creating volatile blend, we're kind of stuck with this. This is something that we won't be able to modify. Then we have drifting abundance across times. If you think of perfume, you have a head of perfume, you have a body of perfume, and then you have a tail end of perfume. So the most volatile compounds are volatilized first, and those are the ones that are enriched in the beginning, and then they're gone at the end, and then the compounds that are less volatile become predominant. So we have this constant drift of volatile composition. And for ACP, because we do know that certain volatiles have to be in just the right ratio, for ACP, we're going to have this brief period of attractance that's maximized, and the rest of the time, it's not going to be optimized. And the effect of the lure will be diminished. Then we cannot control volatiles individually. Let's say if we have our lure composition and we think that that's why a particular volatile is more important, and we want to see how it changes, if we want to increase this concentration, decrease this concentration. The only way we can do that is make a bunch of different blends to have different concentration of this particular volatile. It's difficult, expensive, very practical. And if it's just one volatile, it's already difficult. Imagine they have dozens or hundreds of volatiles like we have in real biological mixes. It becomes essentially impossible, definitely impractical. And then, of course, a practical to optimize composition for complex mixtures. And this is something that directly stems from the previous point. If we have a really complex blend and we try to optimize this to make it the most attractive possible combination, the number of possibilities for different blends is essentially infinite. So if we are to be making that in sort of any comprehensive manner, it will become impossibly expensive and cumbersome problem to solve. So this is something that hasn't been really done, and optimization has been done only on a handful of compounds, unfortunately. But this is, again, this is a limitation of the current technology. There is, of course, obvious solution to that is dispense each volatile individually. So if you have a blend of however many volatiles that we want to test, and we have some biological rationale or evidence from previous research that those volatiles are important for ACP attraction, we can easily disperse each one by one, and then we can turn it off. We can control it in abundance, and then we can make these blends dynamically controlled at any point, so we can directly read out a response of the insect and see what's the most attractive blend. So the problem here is that it's very expensive to do so, right? Because if you have dozens, but then again, hundreds of volatiles are more realistic for natural blends. If you have hundreds of volatiles to be controlled, we have to have hundreds of valves, hundreds of dispenser units, and each one have to be controlled individually. That makes it extremely complex and cumbersome. This system will be very difficult to manage. It will be really expensive to produce, and will be very complex in operation. We're going to have multiple, release devices, multiple heating units, and things like that. Some volatiles are, maybe two volatiles. So we have to have some kind of cooling device to keep volatile in place and not let it, disperse fast enough. All of that leads to engineering challenges that haven't been solved up to date, and this is the reason why we don't have a device like that. So our research centers around potential solution, and this solution is based on novel graphene material for controlled volatile release. So let me give you a little bit of background on what this material is and why we believe that that would be a solution. I would imagine that everyone heard about graphene. It's this magical material that a few years ago Nobel Prize was awarded. The graphene is essentially a sheet of graphite that's stretched out as a single layer of carbon atoms arranged in a hexagonal pattern. So the material we're talking about is the material that has been developed by a colleague of mine and someone who's part of this project, Dr. Douglas Adamson. They develop a graphene foam material. So on the left here, you see the microscopic picture. That's what material looks like. And if you continuously keep zooming in, we see that it's made out of little bubbles. And these bubbles are coated by these flakes of graphene material, and they actually confirm with ST imaging that this is indeed graphene. And because graphene is conductive, this overlapping intercalated sheets, they create this 3D network of graphene within the body of the material, the bulk of the material. And this way of arranging graphene sheets imparts properties of graphene to this polymer composite, which means that it is conductive. And because it's such a high surface area, it acts as a sorbent. And this is something that we have showed, and my video is not starting, but basically what this video is showing that this material acts as a porous wick. If we have our compounds on the bottom, it soaks it up and it kind of moves up to the top. But then, because it's conductive, without any metal or anything like that, we can just connect a pair of leads and apply voltage, which leads to instantaneous Joule heating. So we can heat it up, and that leads to desorption. What's really different about this material is that it's extremely cheap, because this is one of the major bottlenecks for graphene application in technology. Graphene is extremely expensive to produce. It is tens of thousands of dollars for gram amount. So this is something that really stymies its application in practice. In this case, the polymer material is made by simple shaking of the monomer of the polymer with the graphite, which is really, really cheap. And so there is a shaking part where you create this emulsion, and then it's polymerized to create this emulsion with the graphene intercalated within the polymer. It sounds really simple, but it's actually much more complex than that. There is quite a bit of know-how how to do that, but that being said, because the input material is so cheap, this is extremely, extremely cheap material as an end result. And so we do have evidence that this is indeed a 3D graphene structure, but it's made for pennies on the dollar compared to the conventional graphene material. Which means that we have this capability of using all the graphene properties for whatever we decide to do. And in this case, we use it for controlled volatile release. So basically, instead of using different valves for different compounds, we use our graphene material as a wick that holds the volatile material, each individual component, and then just applying simple voltage by a current controller, we can control individually all these different components, and then we can blend them together in the mixing chamber and then release them as a composite smelt. That can be changed both instantaneously and in a highly controlled fashion, because all it needs to do, we just need to increase or decrease voltage. Once the voltage is removed, the volatilization stops, because graphene polymer is a really strong sorbent, so it retains compounds very, very efficiently, even the really volatile ones. And it can be powered by solar panel if needed, and I'll speak to that a little bit later. So this is a idea for our current QSDA project, and there's a lot of work that has been done under that. But I want to sort of quickly give you a little bit of overview of what we've been doing. One of the things we've been doing is where we're actually testing the volatile composition and the properties of graphene, how the volatiles are released. We have mass spectrometry in my lab. So my lab is metabolomics lab. We do chemical analysis using gas chromatography mass spectrometry, liquid chromatography mass spectrometry for volatile and non-volatile compounds, respectively. So GCMS is the best way to see what's the composition of the gas phase. So we have a polymer used for sampling headspace. So this is something that's used quite often. PDMS stands for polydimethyl siloxane patch. This is a common sorbent for headspace sampling. So we can sample wherever the volatiles are produced from our composite by controlling voltage in certain ways, and then we can create this plots where we can see how volatile is released based as a function of voltage or any other parameters. So this research has been going on for over 2 years now, and I'm going to summarize this complex and large body of work in 2 slides to make a very important point that I believe is instrumental to understanding how this material behaves. Notice how here we have a DC voltage. So this is 20 volts DC, so the direct current applied to graphene. And we have volatile release that is actually lower than we take a square waveform. So basically 20 volts here is applied a 50% of the time duty cycle. So 50% of the time the voltage is on, 50% of time the voltage is off at 1 kilohertz frequency. And we see we have more than double rate of release. What it tells us is that this is not just a thermal desorption. And if you look at the plot at the bottom, when we have a DC current, the composite gets much hotter as opposed to AC current, or the waveform current, but the release is actually greater. And the temperature, the plot in the upper right corner, the temperature here is much higher for the DC, and it's significantly lower, around 60 or so degrees for the AC application. And this is general acetone, which has much higher boiling temperature than 65 degrees or so. Something like 198 degrees centigrade, I believe, is the boiling temperature, which tells us that this is not just boiling of the compound of the composite. This is a quantum behavior that we're observing, and we don't have full picture of what exactly is happening here. But what we believe the difference of this composite is that when the molecule is observed on the surface of the composite, and we apply current, the energizing of the molecule happens through some kind of energy transfer by basically exciting it into the excited electron state and then desorpting it using that excitation as opposed to thermal excitation when we supply energy as a thermal energy, which means 2 things. First, we are volatilizing compound much more efficiently because we don't waste energy on the thermal excitation of the molecule. And second, when the molecule is excited and partitioned in the gas phase, it's not hot, quote unquote. It's a volatilized molecule, but it's still not thermally excited. And this is probably one of the major differences of this composite from just a regular, pulling off of the weak approach. Notice how, because this is 1 kilohertz frequency leads to the best release, we probably tapping into the time scale of this event, which basically a time that required for the molecule to get desorbed, a new molecule to get absorbed out of the bulk to the graphene, so partition from the polymer support to the graphene material, and then gets excited off graphene into the gas phase. So the bottom line here is that we have evidence that we can highly efficiently volatilize compounds at the very low power and really low temperature. And low temperature is important because high temperature leads to all kinds of undesirable effects, like material itself can crack, for example, or we can start burning off these molecules, chemically degrade them or something like that, which is obviously going to lead to diminished attractants to the insect. So this is what the first prototype looks like, and this is 3D printed device where we have, in this case, we have 6 compounds that are sitting individually with the graphene release unit, and then we have a mixing chamber that is releasing the compound mix out of the exhaust, and then we confirm with GCMS that we can control precisely what comes out of this device. So this is an example. We have 6 compounds, 3 of them are on and 3 of them are off, and so for the ones that are off, we have nothing. For the ones that are on, we see clear release in the gas phase, and here we have 2 stereoisomers. That's just the impurity of the compound that we got from the vendor. All right, so this is the technical part. Now I'm going to talk about the biology part, and the biology part is the choice bioassay that was done by Lucas Stilinski's lab in the University of Florida. So in Stilinski's lab, they used the T-nasal factometer to quantitatively measure insect behavior as a response to volatile or other cues. So we have our device here connected to the T-nasal factometer, and then we have a control arm where we can add just blank humidified purified air, or we can put actual citrus tree, which is the highest possible attraction that we know of to the ACP. And this is what it looks like in actual setup. We have a light above the T-nasal factometer. And light is necessary because insect naturally tries to orient itself to the sun, so it goes upwards toward the light. And this is to kind of lure insect to go up the olfactometer. Okay, so the experiment that Stilinski's lab has been conducting is the choice bioassay, and there are three possible outcomes for the insect. So the insect can go into the control arm, and that means nothing's really happening. So there is no clear attraction or repulsion of the treatment arm. And this is probably the least desirable outcome when there is nothing really happening worth noting. Then if it goes preferably into the treatment arm, that means there is attraction going on. So the treatment arm is more attractive than control, and the insect is selecting at higher frequencies, which means that it is attracted to whatever the smell is coming out of the treatment arm. And then the third outcome is the insect is being suppressed from going upwards into the T-meso olfactometer, and this is repellency, because the insect is not entering the T-meso olfactometer even though it wants to, because it has three natural inclinations. It wants to move toward the light, like I said, because it orients itself by the sun. It wants to move upward, and it wants to move upward toward the water. So if you have water, like let's say from citrus tree or treatment, it wants to go upwards. And if it cannot, that means it's suppressed from doing so, and so whatever the smell will give to insect is a repellent. So this is an example of data that Stilinski's lab has been getting, and this is just for one single compound. We see that we have attractancy and repellency. So formic acid is a repellent in this case, and this is weird because it's supposed to be attractant from literature. It's probably because we're releasing at a really, really high concentration, so it crosses the threshold when it becomes repellent as opposed to attractant. But methyl salicylate is a known attractant to ACP and many other insects, and that one is clearly an attractant. And by the way, the no response rate here is about 15% or so, 10-15%, and that's very normal. That's what is expected in these type of experiments. What is not normal, what is not expected, this attractancy of over 60% is not expected at all for a single compound. This is not something that Stilinski's lab has ever seen. So as even a single compound from this device somehow creates abnormally high attractancy to the insect that probably stems from the way that attractant is released. So when we get to the release of multiple compounds, oh yeah, acetic acid is another attractant. When we get to release of multiple compounds and we can do optimization, we can hone in on blends that are far more attractive than single compound, of course. So let me walk you through this slide. So this slide basically shows attractants on the left side, repellents on the right side, on the middle, and then release arm, meaning the insect is not moving and remains not entering T-meso olfactometer on the very right, the orange color. So citrus flush is our positive control. This is the most attractive thing that we know about, and citrus flush should be attracting insects toward the treatment arm more often than not, and it does. And so 75%, that's roughly what we expect. That's consistent with all the previous experiments, and this is something that confirms that the insect is doing what it's supposed to be doing. Then we have blank, and the blank should have no behavioral response, and it is indeed the case. So insect chooses left or right arm with the same frequency, and it has also roughly equal probability to stay in the release arm, so not going anywhere. Again, consistent with what we would expect to be happening. So the blends that show high response on the treatment arm are attractants. So we have 4 blends here pointed out by arrows that are clearly attractant. And the one that really is interesting is formic plus acetic acid, because if you look at it, this is attractants on par with actual citrus tree with only 2 compounds. And those 2 compounds are preferential because they're really cheap and they're really easy to volatilize. And this is something that we were not expecting at all, such a massively high attractants. And then, the choice of control arm is even lower than on the citrus flush. Again, this is something that was not expected at all, because this is only 2 compounds. We don't even have to go to really complex blends. Just the device itself is creating volatiles that are far more attractive than was expected before. And then we can test repellent. This is example of repellent. So the fur oil is example of non-repellent, and it's made mostly from monoterpenes such like pinene or carine. And as expected, we mostly suppress the desire of insect to go upwards, and we have more insects staying, not entering the olfactometer than going upwards. But this is actually so effective that it entirely suppresses the desire of insect to go upwards, even when there is a citrus flush offer, which means that we can completely override attractants to the citrus flush using synthetic chemical, or in this case, it's natural chemical, but the same idea. So this is something that we have done in the laboratory. So what's happening right now is Stilinski's lab is actually testing this device out in Orchard, CREC facility at University of Florida. This device is small, so this is the second generation of the device, and this is the first generation of the device. Because it uses such low power, 12-volt battery will last it for days, and if you give it solar panel, then it becomes fully autonomous. You can stay in the orchard forever, as long as you have volatiles. So we don't have results from orchard yet, but basically we want to show that this attraction translates from the laboratory to the orchard, and hopefully we'll have updates fairly soon. But the problem is that Stilinski's lab has been beset with all kinds of problems, and they lived through 2 hurricanes, and one of the hurricanes actually destroyed the device. It was not moved out of the orchard. So we do know that hurricanes are bad for electronics. Surprise, surprise. But this is something that hopefully is going to happen within a few weeks. So up until this point, it was the actual results from the project. Now I'm going to talk a little bit about future directions and the way I personally envision the use of the technology in practice. And this is not a description of the results. This is basically me waxing poetic about what can hopefully happen going forward. So first off, and this is something that we were envisioning as the original application of the device, is the machine learning or artificial intelligence-based optimization of smell. So the way we envision that to be happening is that when the mix generator, the volatile mix generator, is connected to the attract and kill device has a psyllid counter, some kind of screen underneath. Once a psyllid gets into device and feeds on the pesticide, on the bait, it dies, falls on the screen, and then I have a pixie camera that is designed to count black specks, so we can use that as our output of the number of psyllids that have been killed. And then we have a feedback machine learning approaches that respond, that basically send this information to the volatile generator, and that it dynamically responds to the input to adjust the output of the device. And this is something that has been widely studied area of mathematics. So, for example, there's a specific algorithm that does optimization. It's called multi-arm bandit. It's kind of like in the in Las Vegas in the slot machine. What input is required to get the best possible output. So volatiles would be our actions, and the number of kill psyllids would be payoff. And we can optimize it in dynamic fashion. Set this device in the orchard, let it sit there for some time. And until we accumulate large enough statistics on psyllid kills, we can come up with the best possible blend. But it's not just the most attractiveness. In this case, we want to maximize psyllid captures, yes, but we also want to minimize the use of expensive, hard to procure compounds, because if you're using something that's really, really difficult to procure and it's too expensive, it's not going to be practical. So basically, we were looking for best cost efficiency point, the volatile mix that works just well enough, but it's preferably cheap, so it can be used practically in larger scale. Kind of like what we did with the acetic and formic acid, because if that translates into the orchard, if or when it translates into the orchard, this is just about the best attractant we can think of, because it's so cheap and non-toxic and easy to procure in large quantities and all that, so it satisfies all the criteria. Another aspect is how we exactly going to deploy these devices, and this is entirely just my speculation. I have no idea, and this is something we haven't thought through, and this requires future research. So the way the device can be used is as attractant and as repellent, as we show. So let's say the scenario when the attractant is in the middle of the orchard and the repellent devices are in the perimeter of the orchard. This way, we basically prevent any other insects to be entering orchard, and we push all the insects toward the middle of the orchard, the central point where our attractant is vacuuming them out. Or we can do it by vice versa, in the reverse order, when we have repellent driving insects out of the orchard, and then we catch them on the perimeter and then kill them on the perimeter. And right now, I don't know which approach is better. And the push-pull attraction of insects is its own area of research, kind of walks that I'm not qualified to speak about that. This is just me sort of voicing that out. And if you have some thoughts about that, I would be very happy to talk. Then another aspect of the economics of this, so the cost of this approach. So this is sort of back of the napkins calculation. Device itself costs about $300 to manufacture using 3D printer, and graphene manufacture costs pennies. The release units will cost like something like 40-50 cents to make. So that's really, really cheap. And $100 of this 300 is a solar panel, which is the bulk of the cost. So the cost of device is pretty much inconsequential unless we do them in a really large quantities, but then the cost can be brought down when it's mass produced. The volatiles, this is the best case scenario. So like acetic acid and formic acid, let's assume it works as well in the orchard as it does in the lab. Acetic acid and formic acid are some of the cheapest compounds to procure. They can be procured in large 50-gallon drums, and if you scale it over the entirety of the orchard, and you basically calculate the amount of volatile that's needed to create continuous concentration over some period of time, it ends up to being something like 0.2 cents per acre per month, which is, again, non-consequential. Repellent, the fur oil, if you do buy it currently, it costs something like $10 per 30 milliliters from the scent manufacturers, like the perfumery companies. Obviously, this number can be reduced by a lot when it's scaled up in a large operation. But if we use the current price, it ends up something like $6.5 per acre per month, which is more substantial, still kind of low, especially if you compare it to the cost of pesticide application. So there is this, large question, because per month, like how do we know that the insect has to be trapped over a month? And this right now is an unanswered question. Maybe it's going to be much less. Maybe it's going to be only a few days, and that's enough to completely eradicate insect in the orchard because it's going to be attractive, efficient enough. Or maybe it's going to take entire year, or maybe it's going to be continuous. We don't know. And if you do it continuously, then this cost needs to be prorated per year, and then it becomes 12 times greater. It's already less inconsequential, but still comparatively low. And but that's a contingent on acetic acid and formic acid to be the attractants. We can use much more expensive attractants, and this is an example of the spotted wing Drosophila. And by the way, I didn't realize that this is one of the major pests, and it's major concern for all kinds of crops. Because I'm not an entomologist, but it turns out that it's a massive pest that needs to be controlled in a way similar to ACP. So in this case, we have a list of volatiles that have been established as attractive to this insect in this paper here. And this list of volatiles is more expensive. It's not something that's produced in bulk, but none of them are super difficult to procure. Those are fairly common. Still, they cost in hundreds of dollars per 100 gram or so. So if you do the same calculation, basically the layer of air in the orchard and the area of the orchard, the volume of the air that we need to be saturating with this compound, we end up with something like $150 per acre per month, which is much more of a cost. Keeping in mind that, again, these volatiles, of course, are more expensive now. If we are to use this approach in large scale, obviously the economy of scale will scale it down quite a bit, probably orders of magnitude. So that will become much, much less. That being said, all of this right now is just hypothesis, and it's not something that I have hard numbers to back up, whether a month is sufficient or not. And it's probably going to vary for the insect. And let's say even if we do stick with this price, for high value crop like raspberries or strawberries, it's still probably going to be economically viable as opposed to blasting everything with pesticides. Okay, so in the summary, this is something that we do know at this point. We have a experimental validation that this graphene-based release approach is indeed feasible both for attraction and repulsion. This is something we have shown in the lab, and we can show that we can precisely control volatiles. Again, both for attraction and repulsion volatiles, we can control it instantaneously, turning it off or turning it on, and we can change concentration in the broad range, and again, instantaneously, which means we can dynamically optimize or change concentration however we want. The blends that we've been tested were as attractive as authentic citrus leaf flush. This is the best we can possibly do. And then repellent can completely override attraction to citrus flush. Again, this is the best we can possibly do. And this is an important point because of the way the volatiles were released in terms of the chemistry of the process, physics of the process. the efficacy seemed to be exceeding conventional release approaches very quite substantially. And there is more research that needs to go into that to understand exactly how it's happening, but we have evidence that that's to be the case. Okay, now this is something that we might need to know, or might need to look for. Maybe not might, but definitely will if this technology to be used practically. So, what are the applications of the technology? The aspects that we need to look into. So the optimization of device performance and optimization volatile mix, that's a sort of separate use that can be done maybe in the laboratory or in the controlled orchard environment just to develop the best possible volatile blend. And this can be used not to only develop the most attractive blend for a particular orchard, particular weather, particular local environment, but also stay a step ahead of the insect because kind of like insect develops resistance to a pesticide and becomes immune to it. Let's say insect develop resistance to our blend and it becomes unattractive to it. We select for population of the insect that is not attracted to that anymore. We can stay ahead of the insect 1 or 2 steps ahead, constantly reoptimizing mixtures, constantly developing new formulations that will remain attractive to the insect. Then there is, of course, practical application differences for deployment in Florida, where we want to suppress population, versus California, where we want to monitor the population and see the insect when they're present, but basically count them for capture and testing purposes rather than try to remove them because there are still, very few number of psyllids in California. Now, it's probably going to change with the season because the smells in the season change and the behavior of the insect change, where they're mating, the oviposition and all that. It's probably going to affect their preferences. And then, of course, like I said, population reduction versus monitoring. And in Texas, it's probably going to be a combination of both. So in California, so if the device is being tested in Florida, in California, we want to test this device for monitoring with the Alliance of Pest Controls, who are interested in collaborating with us on this. The question of economic viability, how many devices need to be deployed, what volatiles need to be used, and when it becomes sustainable for farmers to use in large scale. Right now, this is all hypothetical. We need to have hard numbers to back that up. And of course, this is shown to work for ACP, but the ACP is not the only pest out there. So aphids or spotted wing Drosophila, those are 2 really important pests that needs to be controlled. Or even beyond agricultural pests, like Ixodida, which are ticks, major problem here in Connecticut, or mosquitoes. Those are probably some of the most important insects to suppress population of. So at this point, we have established the company, actually a few days ago, that will be commercializing the technology, but there's a couple pieces of research that needs to be done to bridge the gap between the proof of principle for prototype to the actual practical application. And that's always the hardest part. So right now we're going to be facing the most challenges. And I am, really excited to discuss this type of, like what is the path forward with the people who actually do that and maybe have some good ideas on that. So in conclusion, I want to thank my lab and especially Ali, who was the lead on this project, and then Douglas Adams' lab. They're the ones who developed the composite. Ali Bazzi is the engineer who created the device, and then Lukasz, who is an entomologist, of course, and he's been testing all the biological applications for us. And big thanks to funding for USDA that has funded development of this device, and big thank for everybody on the call and in the audience to listen to me, and I will be happy to take any questions.
For him. Nope. All right. I think we are good, Dr. Aksenov. Thank you so much.